Let's bring up our next speaker. Oh, wait, he's already here. So this is an AJ doubleheader. So today, AJ will be presenting his second talk on compiler support for sparse tensor convolutions.
Yeah, sorry if you're sick of me. Peiming could not attend, unfortunately, but this was more work done with the Google Sparsifier team, spearheaded by Peiming, who should get all of the credit and all of the hard questions. So I put his new email because the email on his paper is no longer accurate. He's busy working at Chris Latner's new startup. So that's why he couldn't attend today. And this was also in collaboration with Anlun, Yinying, my advisor Fred, and Aart, who headed the Google Sparsifier team. So why do we care about sparse tensor convolutions? Well, convolutions are everywhere. They're extremely common operations in image processing and machine learning, and they're more traditionally looked at as blurs and convolutional layers, but they also appear in max pooling and average pooling. So they're really these like windowed computations over an array. In the language of tensor algebra, which I showed in the last talk, they're represented by these compound index expressions, where I've highlighted in red the places where an array is indexed not by like a loop variable, but by multiple loop variables. So this is why convolutions, where convolutions exist, but why do we care about sparse convolutions? The answer is typically sparse machine learning, but the way that sparse convolutions show up in sparse machine learning, there are multiple ways. So one is the sparsity can be produced by an activation function like ReLU that produces a lot of zeros, or they can be inherent to the input. So this can look like sketches, like convolutions over sketches, or convolutions over point clouds. But why? So this is where they show up. Why are they difficult? Well, I want to start with what a dense convolution looks like. So with the 1D example that I showed on a previous slide, the dense computation looks like this nested for loop, where there's an iteration over n, the length of I, and an iteration over j, with a summation here. And so this is an O of n times k, iteration. But what if I is sparse? The naive thing to do is to just insert a check where, if I has an element here, then do the accumulation. But this still gets us an O of n times k runtime. And this is not ideal, because one of the benefits of sparsity, besides the memory saving benefits, is actually saving in computation when the input has zero values. So we're not the first people to notice this, and there was actually a paper last year, Taco UCF, in MLSys, which is some great work by Juan et al. And they figured out how to lift that if statement to really sparsify the J loop. And so what that looks like visually is they iterate over a 1D vector, applying this shaded 2 block is f, and the sparse thing is I. And they iterate and repeatedly have a skip computation when there's no non-zeros in the section that they care about. And so they keep going, and this achieves a better runtime, especially when k is quite large. This asymptote is quite nice. If the fractional math looks scary, it's just the average work per iteration of the sparse J loop. But we can actually go a little bit further. So we can sparsify both of these loops. And that's what this work presents. And we show how to do this via multiple iterators, so it's no longer just one iterator per loop. And I'm going to get into like the concrete details of how this works, but I want to show you some visual intuition beforehand. So when we're iterating over I, we first compute one element of the output here. And then we sort of skip forward to the next non-zero subsection. So notice that I'm not saying the next non-zero, I'm saying the next non-zero subsection. So this is a case where f applied to I, some element in I is non-zero. We're not just skipping to the next non-zero. and then we step forward. And this gets us a pretty nice runtime that is completely devoid of n. This is a runtime based on the number of non-zeros and the dense value k, which is typically far less than n. And this really highlights the key idea of this paper, which is that we want to iterate over non-empty subsections. And you can do that. And I'm going to show you how. But first, I want to show that this actually leads to some pretty real-world speedups. So we evaluated ResNet 50 with MLIR sparse, which is this work, compared to Taco UCF, the prior work. And we show some modest 2x speedups at around 90% sparsity, all the way up to 20x speedups at high sparsities. And this can get even larger at much higher sparsities. But you might be asking me, why is this hard? Why are solutions only coming out, this within the last 24 months? If you remember from the last talk, any solution to a sparse array programming problem needs to be polymorphic over sparse data structures, and there are a lot of them. So our solution is, once again, an iterator model. So we define 5 primitives that represent iteration over non-empty subsections. And I'll show you first how we use this in the 1D example, and then I'll show you how these are actually implemented. So in the 1D example, we first start by finding the first non-empty subsection. Not the first non-zero, but the first non-empty subsection of size k. And then we have a loop that iterates as long as we have more subsections to iterate over. We can compute I via this subsect offset primitive, and then we can iterate over j using the subsect iterator primitive. And then at the end of this loop, we would both write to the output and step the iterator forward. So what does this look like on a concrete data structure? Well, suppose we have the following compressed vector that has 3 elements, A, B, and C. The way this would be stored in a compressed vector is we store the 3 values, and then their 3 coordinates. If we want to implement the subsect iterator model on this compressed vector, it looks something like this, which I don't expect you to read all of this code. I will zoom in on the important parts. So when we're initializing our iterator, we first initialize two iterators. The first is a position iterator, and the second is a logical I iterator. So I starts at 0, and P starts at the first non-zero value in this case. If we want to know whether or not we've gone off the end of the subsection, all we have to do is check whether or not I has progressed past where it can be. So this is the bound on I. Subsect offset is just returning I. And subsect iterator, which is how we iterate over J, the inner loop, starts the iterator at P. So that looks like this. And returns the value of the coordinate of P. So it would return J equals 0. Offset by the value of I. Then we step JP forward here. And that value is more than k away from our current value of I, so this while loop breaks. If we want to get the next non-empty subsection, there's a conditional that says that if I is behind where P is right now, we just step I forward. But otherwise, that just means that there's a big non-empty chunk behind the current position space. In this case, that's not the case. So we actually go to the second branch of the conditional, and we step P forward. And then we jump I forward to the first value of I that we have not iterated over before that is behind P. So that looks like jumping I to the element behind P. Behind B right now. And then, if in the next iteration of the loop, we want to iterate over all of the non-empty J values, we're once again going to have this JP iterator highlighted in the boxes here. And we yield the value J equals 1, because that's the offset of where P is from I, logically. So then we step forward, and we've gone off the end of the array. But you might be saying, well, OK, AJ, that's great. You can compile like a 1D convolution, sparse convolution. That's nice. well, we know that that's not all that people want to do. Like I said before, there are a lot of operations that you want to do in array programming. And we develop compiler technology to sort of reduce convolutions to the Taco compilation framework. And so there are a lot more details in the paper, and I'm happy to talk about it after the session or during the Q&A. But I want to talk about the impact that this system has first. So we handle considerably more than just 1D convolutions. The iterator model extends to higher dimensional convolutions. It extends as far as you want it to go. But it also composes really nicely with other operations, like shape operators or the standard tensor algebra that is implemented via the iterator model in Taco. So looking at the first of these bullet points, if we have a 2D convolution, we can once again just apply the iterator model, first over I, then over j, and then over the inner variables k and l. And this just sort of naturally extends to iteration over a higher dimensional, a windowed iteration over a higher dimensional array. Now you might be, if you're really glaring at the slide, you might notice that there's a loop ordering denoted here. So I want to take a quick aside and talk about loop ordering. This matters both in the dense world for axis patterns, but it also matters in the sparse world as well, also for axis patterns, and sometimes for asymptotics. So as a result, we actually made loop order user schedulable in our system, and we evaluate in the paper both the qualitative and quantitative trade-offs of different loop orderings. So this is a side-by-side of what the different code looks like, but we also perform evaluation for the different loop orderings. So for 2D convolutions, we compare against the dense case because Taco UCF actually can't do 2D convolution over these data structures. And we see that compared to a very, very nice dense convolutional framework, we achieve a crossover point of about 80% sparsity. After that, our system is faster. And there's more evaluation of 1D and 3D in the paper. So that's great. But convolutions aren't just higher dimensional. Sometimes you want them to compose with other operations, and the iterator model really does compose. So consider this sort of odd looking convolution. We have this compound index pattern in C, but we're just adding B to windows of C. So visually, that looks like this. We're producing a 2D vector from adding a 1D vector to windows of another larger 1D vector. Computing the first row of A requires taking the first row of B and adding that to the first window of C. And we just step forward computing on these windows of C. Notably here, we skip over computing a row of A when there's no element in B and there's an empty chunk in C. So we get nice asymptotic performance for these computations. So that's good. What does the generated code look like? Well, it really follows the iterator model from the last talk and this talk. We first initialize some iterators for B and for the subsections of C. And then we iterate while those iterators are still valid. We compute I and J, and then we have some control flow for handling the case where B is empty and C is not, or C is empty and B is not, or they both have non-zero values. And then we conditionally step our iterators forward. If this looks familiar, you may have seen Taco papers before. This is exactly what Taco generates for vector addition, modulo the fact that there's a subsect iterator instead of just a regular vector iterator. So I think I'm also running a little bit low on time, so I'm gonna finish with some concluding thoughts. I really want you to take away that asymptotically correct sparse convolutions can be achieved through a rather simple iterator model. And that iterator model composes really well with prior and concurrent work in sparse array compilation. And achieve some very real-world speedups on real-world kernels. Also, Peiming upstreamed this in the MLIR sparse dialect, so it's very open sourced and very testable if you want to find bugs in it or something. So yeah, I'm happy to take questions. And like I said, maybe I was joking about the hard question. I can take hard questions, but if you have really hard questions or big compliments or something, email Peiming. I've put his email on the slide. So yeah, thank you.
Again, very nice talk.
Thank you.
So in the performance results that you had, so between the MLIR and the Taco UCF,
Taco UCF, yeah.
Yeah. So even for the smaller sparsities, there were some performance improvements. Is it because of some artifact of MLIR implementation doing more optimizations?
I'm not sure I understand the question here.
So okay, I misread it then.
Oh, okay. Yeah. So sorry. Maybe I should have spent a little more time on the slide. So red is Taco UCF, gray is us, and then yellow is a log plot of the speedup.
Okay. So you have a speedup already here.
Yeah, we see like a rather modest speedup at 90%, and actually beforehand, we see a fairly decent speedup.
So is it an artifact of the MLIR implementation having some optimizations that the Taco UCF doesn't?
So this code, if I remember correctly, should theoretically see like an asymptotic speedup because the generated code for this particular kernel is asymptotically better. Sometimes asymptotes don't mean everything, so we don't see like an asymptotic speedup, but we do see a speedup that is like less than asymptotic. We don't exactly like know what it's probably a memory like problem where you can only load memory so quickly.
Yeah. Okay. Thank you.
Any other questions?
Well, great. So maybe you can comment just again on the on possible parallelisms, not particular with what you're doing here, but in the context in which these kernels are generated. So do you? I guess you somehow need to make use of parallelism.
Yeah, so actually, I don't show this in the slides, but we are able to generate parallel code for this particular implementation, and Peiming put a lot of work into that, and Taco UCF also can generate parallel code. The current state of the art for, or at least the way I understand most parallel code generation for sparse systems is whenever you have a dense loop, because like maybe your data structure is CSR and there's a dense loop over I and a sparse loop over J, you can often like parallelize the I loop. There are no like loop carry dependencies or anything like that. So it's really when you have like some sort of like some amount of density, you can perform parallelism, and I believe that's what we do, and that is what Taco UCF does as well. When you have just like rampant, completely irregular sparsity, it's pretty hard to do parallel loops because you don't have for loops, you have while loops. And like in general, we don't really know how to easily parallelize while loops, I think. So we do perform parallel code, but it's like the simple case of like having a dense for loop. Cool. I think there was one last question. Is it okay if I take that, or are we out of time?
I guess my question is partially answered in the previous question, but my question is, does it support like Taco scheduling language in general, maybe loop ordering, loop reordering, loop tiling, those kind of advanced optimizations?
Sorry, can you repeat the first part of your question? I heard the last part, but. Oh,
yeah. I just wonder whether it supports the Taco scheduling language.
Oh, yeah. So it does not support the full. So MLIR sparse does not support the full Taco scheduling language. It does support loop reordering. It currently does not support like tiling or anything like that. That's just an engineering artifact of like we haven't implemented the MLIR sparsifier team, not me, has not implemented the Taco scheduling language in that system yet.